Now that we've gotten our feet wet talking about concentration units, we want to apply them. And one of the things we want to start talking about is the idea of colligative properties. Colligative properties are properties of a solution. So first off, colligative properties only talk about solution. And these are properties in the solution that depend on the number of solute molecules, not the nature of the solute. So what this means is basically if I have, how we think about colligative properties is if I have, say, a solvent, water. Water has properties. How do the properties of the water change when I put molecules in there, when I dissolve stuff in there? It doesn't matter what I put in there, anything I can put in there, but how does that number affect? So colligative properties, you probably haven't heard of any of these, or you have heard them, but we're going to, the application of them. But some non-colligative properties are things like color. If you dissolve red food coloring in water, the color becomes red. If you dissolve green food coloring, the color becomes green. So those are solution properties that are based on what you dissolve. Conductivity. For example, electrolytes, when you dissolve them, they make the water conduct electricity. Non-electrolytes don't. That depends on what you are dissolving, not the number of things dissolved. And actually, conductivity doesn't depend at all on the number. Once you get electrolytes in the solution, it dissolves. And it doesn't matter, you can't make it, or it conducts. You can't make a solution double conduct electricity by dissolving more electrolytes. Right? So colligative properties are going to be properties that are properties you can affect and you can change the solvent. So the solvent has some properties. How do you change it? By adding in molecules, by numbers of molecules, and you can make them change even more. There are three colligative properties that we're going to look at: vapor pressure depression, or lowering, boiling point elevation, and freezing point depression. So again, when we talk about colligative properties, these are properties of the pure solvent. Water just has vapor pressure. Water boils at 100 degrees Celsius, and water freezes at 0 degrees Celsius. So what we're going to look at is how do those properties change when you form a solution of that water. When you dissolve stuff into water, how does the boiling point of the water change? How does the vapor pressure of the water change? One note, when we're looking at colligative properties, we are going to make our lives simple. We are only going to look at non-volatile solutes. So non-volatile, remember, volatile are substances that evaporate quickly, things with high vapor pressures. So if you'll notice that vapor pressure is one of the colligative properties we're going to be looking at. We don't want to be worrying about what is the vapor pressure of the solution that comes from the solvent and the solute, because that's difficult. Come back in a couple semesters. But right now we're going to deal with non-volatile. So the solute is not going to evaporate away. One important thing about that is the concentration will not be changing, and we're not going to have to worry about its effect, say, its participation in being a vapor. So solute concentrations are constant. We're going to make our lives easy. When we're going to go through these in more detail in other videos, so vapor pressure depression, when you have a solvent, if you add solute to it, the vapor pressure decreases, the boiling point goes up, and the freezing point decreases. These are always true. This always happens to any time you have a liquid and you dissolve stuff in it. And the motivation for all of these, and the reason why they are colligative properties, is they are all based around the idea that solute molecules take up space. You can think about in a liquid, you have these liquid molecules that are all together. When you go to freeze, say, they're going to take on some sort of position in a solid, but the orange, those little small orange solute molecules get in the way and they prevent forming a crystal, so it doesn't quite work out. And so that's why the freezing point is lower when you form a solution. With boiling point elevation, again, they get in the way. These molecules take up space, they get in the way. That's what makes these colligative properties. It doesn't matter what the solute is. Those little small balls on the bottom, those small solute molecules are just little orange circles, whatever. They always will just be getting in the way because they're not solvent molecules. They mess up the pattern of those solvent molecules from forming that solid. So these colligative properties are all about the number of solute molecules, not what the solute molecules actually are. Ionic, covalent, whatever it is, different types of ions. What matters is how many you have, not what type they are. Along those lines, we do need to be mindful of the fact that covalent and ionic compounds dissolve differently. When you have a covalent compound, a non-electrolyte, a molecular compound, and it dissolves, say for example C6H12O6, that's called glucose, for every 1 mole of solid, you make 1 mole of dissolved molecules. But when you dissolve ionic compounds, electrolytes, you get more dissolved ions than you had compound in the original compound. So, for example, MgCl2, this 1 mole of solid becomes 1 plus 2 gives me 3 moles of ions. So when we're thinking about the these colligative properties, we want to be thinking about, well, how many ions are dissolved in solution? How many actual objects are floating around in solution? Because the number of objects is going to affect how you make that colligative property. Again, it's the number of objects that are dissolved, not what they are. So if we look at this, here are the equations for these different colligative properties, vapor pressure, depression, boiling point, and freezing point. There's a couple of things we can see. First off, there's some new variables that have shown up. I want to point out a couple of them. We have this X of solvent, and then we have this little italicized M. These are different concentration units. So why we're talking about colligative properties here is they are going to motivate why we have more concentration units. Molarity and percent concentration really can get you everything you need for being a chemist or existing in a supermarket, buying stuff in a supermarket. But we have other concentration units that we need for different applications. And as we start to get into some of this more wider variety of things, we're going to have some different concentration units that we're going to use that we need to talk about. The other thing that I want to point out about these is we have this I term that's in here, this italicized lowercase I. This I is the number of moles of particles made from 1 mole of solute. The I is actually kind of cooked in up here. It's also affecting here. This is this idea that ionic and covalent compounds dissolve differently, and we want to account for that in our equations, so we're going to need to be mindful of that. So if we return to our idea of ionic and covalent compounds, for covalent compounds, I is equal to 1. If you have for every 1 molecule in your solid, you get 1 molecule of dissolved in the solution. So solid, all it does is become aqueous. You're not changing the bonds. You're not changing the number of things. In an ionic compound, the I is equal to the number of ions. So this was 1 ion, this is 2 ions, add them together, you get 3. So in this case, I is equal to 3. So if you were making a solution of magnesium chloride and you wanted to look at the colligative properties of it, you would need to account for the fact that whatever the concentration is, you define the concentration based off MgCl2, but functionally there are 3 times as many dissolved particles, so the concentration of total stuff in solution is 3 times higher. And we'll apply this in examples. We'll look more into these colligative properties. Just want to introduce this idea before we start using it. Bringing us to question 2 for participation 127. What is the value of I when each of the following compounds is used as a solute? I have LiF, lithium fluoride, CH3OH, that's called methanol, and ZnCl2, which is zinc chloride. So this is the second question for participation 127, due Wednesday, January 27th at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. What is the value of I when each of the following compounds is used as a solute? Lithium fluoride, methanol, and zinc chloride. All right, just got another question for participation 127. 2 more videos. Will we find any more questions? Let's find out.